So far, we've talked about quite a few different sorting algorithms, along with some of their weaknesses. So in this video, we're going to be talking about how we can combine some of those sorts to make a hybrid sorting algorithm that works as a better general purpose sort, instead of having worst case scenarios that we are hampered by. We'll be using quicksort as the basis for a hybrid sorting algorithm, but as we've talked about before, quicksort really isn't that quick in the worst case scenario. But it does have some room to be optimized if we do a better job choosing our pivot point. And in other cases where quicksort falls short, we can actually utilize other sorting algorithms that are better in those situations. So since quicksort is good at splitting collections into smaller segments, we can leverage something like insertion sort on those parts if we get them split down into small enough segments. This helps reduce the extra overhead of choosing a pivot point and splitting, and it also helps reduce the number of recursive calls that we have to have. So remember, our quicksort has an issue with the Stack Overflow exception if the dataset gets too large. Quicksort is more efficient when the pivot point causes the collection to be split into equal segments. So in an ideal world, if we chose the median, that would help ensure that we have segments that are about the same size for most datasets. But finding the median or calculating the median, especially for, let's say, 1,000,000 elements, is pretty expensive to actually do. So the median can be approximated by using a technique called the median of 3. Here we're just going to calculate the median between the first, middle, and last element of the segment or part that we're actually sorting. Now, of course, this is an approximation, so it doesn't avoid the worst case performance scenario, but it does reduce its chances by quite a bit, especially for very large data sets at a very relatively low cost. But we can completely avoid the worst case scenario if we limit the recursion depth. So what we've done before helps mitigate that, but we're still not going to avoid the Stack Overflow exceptions completely here. If we prevent the Stack Overflow exceptions or limit the recursion depth, we can significantly increase our performance. Depth can be tracked by using a simple int parameter for the quicksort algorithm that we are actually using, or the method that we're actually using. And so once we reach whatever our max depth is, we can say 30 something, right? Once we reach that max depth, we can switch to a big O in log n algorithm like merge sort. But with this and our previous improvements, we'll actually have a sorting algorithm that has better performance for a much wider range of cases and better memory efficiency than algorithms that we've used before.